Hello and Assalamu alaikum. The topic of today's lecture is Zener diode. Zener diode is a type of diode that act as normal diode in forward bias state. This is the diagram of characteristic curve of a Zener diode. We can see in forward bias state, diode is acting like a normal diode. That means it has some Vk here, and beyond that, if we apply voltage greater than Vk, then it will lock here and current will rise like this. And in forward bias state, we can replace this diode with this equivalent circuit. That is, if this is a silicon diode, then we can replace it with a voltage drop of 0.7 volt. Now if you see in reverse bias state, until we apply the voltage which is equal to or greater than Vz, until that point the diode is off, or you can replace it with an open circuit. Now if we apply a voltage that is equal to or greater than Vz, then diode will be on, and you can replace this Zener diode with an equivalent circuit of this voltage source which is equal to Vz. So normally the Zener diode is used in reverse bias region, and practical usage of Zener diode is as voltage regulator. Now to have a deeper look of this Zener diode, we can solve an example in which the circuit which is a series circuit. This contains two Zener diodes and few other diodes. Let's see what will be the output of output voltages here, which we call reference voltages, and let's see how to solve this kind of circuit which incorporates Zener diode. So the statement says determine the reference voltages, that is V01 and V02, which uses white LED to indicate that the power is on. What is the level of current through the LED? We should find the current through this series circuit and the power delivered by the supply voltage. And how does the power absorbed by LED compare to the 6 volt Zener diode? So to solve this kind of circuit, as we can see, this is a series circuit. We should see the applied voltage. The applied voltage, that is here, it is 40 volts. This should be greater than the total voltage drops across all these diodes. In other sense, we should see, is this applied voltage is enough to turn all these diodes on. So to check whether this applied voltage is enough or sufficient to turn all these diodes on, we can see uh, the voltage drop across white LED is normally 4 volt, and voltage drop which is actually Vz of this Zener diode is 6 volt, and in on state voltage drop across this silicon diode is 0.7 volt, and the voltage drop across this Zener diode in on state is 3.33 volt. This is given. So the total voltage drop in this series circuit across these diodes are 4 plus 6 10 volt, and zero point 0.7 plus 3.3 4 volt, 4 plus 10 14 volt. So we should have at least 14 volt applied at input to turn all these diodes on. Here we have 40 volts at input, so we can easily say that this applied voltage will turn all these diodes on. Remember, we use Zener diode in reverse bias. So note that the silicon diode was used to create a reference voltage of 4 volt. So first we can calculate V01, which is reference voltage. So if you want to calculate V01, that means the voltage from this point to the ground. Here we know by this applied voltage these two diodes are on, so voltage drop across silicon is 0.7 and voltage drop across this Zener diode is 3.3. So total voltage from this point to this point is 4 volt, 4.0 volts. So reference voltage 1, that is V01, is 4.0 volt. And reference voltage 2, which is V02, should be 6 volt plus 4.0 volt, that is 10 volt. So V02 is V01 plus the Zener voltage of this diode, which is 6 volt. So 4 plus 6 is equal to 10 volt. So V02 is equal to 10 volt. And the 4 volt across the white LED will leave the voltage of 40 minus 14 volt equal to 26 volt across the resistor. Why we are calculating this voltage across the resistor? Actually, we want to calculate the current through this series circuit. So if we note that 4 volt gets dropped against this white LED and 10 volt from this point to this point, so total of 14 volt is getting dropped from this point to ground, that is from white LED to ground. The remaining voltage will appear against this resistor R, that is 26 volt will appear against this resistor R. So from this we can calculate the current through this resistor, which is actually series current IR through Ohm law. We can calculate this current 26 volt by the value of this resistor, that is 1.3 kilo ohm, is equal to 20 milliampere. So 20 milliampere current is flowing through this series circuit, that is from all the diode as well as the through the resistor. Now if you want to calculate the power supply, total power delivered by the supply, we can calculate this by simply P is equal to Pi, that is we have 40 volt Vs or Vi and 20 milliampere current is getting drawn from this supply, so 20 milliampere Vi. So the power delivered by this supply voltage source is 800 milliwatt, 40 volt into 20 milliampere, and power absorbed or dissipated by this LED should be 4 volt into 20 milliampere. As we know, 20 milliampere current is flowing through the LED and 4 volt is being dropped against this LED. So VI 4 into 20, 80 milliwatt. And power absorbed by 6 volt Zener diode is 6 volt into 20 milliampere current, that is 120 milliwatt. So the power absorbed by Zener diode exceeds that of LED is by 40 milliwatt. This is how we solve a circuit which incorporates a Zener diode. Now if we see a voltage regulator circuit, which is a Zener regulator circuit, there are three different conditions for the analysis of basic Zener regulator circuit. The first condition is when we have Vi and load resistor RL both are fixed. In this circuit, this Vi and RL both are fixed. To do analysis of this kind of circuit, we have few steps. The first one is we determine the state of Zener diode by removing it from the network and calculating the voltage across resulting open circuit. That means we remove this Zener diode from the circuit and calculate the voltage against this RL, which will be actually against this open circuit, to see whether the voltage appearing against this RL is greater than or equal to Vg to turn this on, or it is less than Vg, so we can say diode will be off. So if we remove this and replace it with open circuit, we are left with this series circuit. For this series circuit, we can find the voltage at this point, which is against RL, which will be equal to V by simply voltage divider rule, because this is a series circuit and two resistors are in series. So by voltage divider rule, we find V is equal to VL, V is equal to VL, RL into VI over R plus RL. Now after calculating this voltage, if this V is greater than or equal to Vg, then the Zener diode is on and we can replace this Zener diode with an equivalent model. And if this voltage is less than Vg, then we know the Zener diode is off and we replace Zener diode with an open circuit in this network. Next, we substitute the appropriate equivalent circuit and solve the desired unknowns. So let's assume the Zener diode is on, that is V is equal to uh, that is is equal to or greater than Vg. So in this case, if this Zener diode is on, we replace it with equivalent circuit of Vg. In that case, we have VL is equal to Vg because we know the voltage remains same in parallel. Now we can find VL, that is voltage across load, that will be equal to Vg, and the current through this R, that is total current in this circuit, is equal to IZ plus IL. Current IR is getting divided in two branches, IZ through Zener diode and IL through load resistor. And we can find IZ from this equation, IR minus IL. And IL is equal to VL over RL, VL over RL, and IR is equal to VI minus VL over R. So IR is equal to VI, which is supply voltage, minus the voltage at this point, which contains two parallel branches, VL, and divided by the value of this resistor R. And we can find the power being dissipated by this Zener diode through this equation, that is Vz if the diode is on, and the voltage will appear across, this will be Vz, and multiplying that voltage with Iz, that is current through this Zener diode. Now let us solve an example of this circuit, which is Zener regulator circuit. For the Zener diode network, determine VL, VR, IZ and PZ. In this network, we have RL of 1.2 kilo ohm. So for the first step, we redraw the network while removing Zener diode to check whether the applied voltage makes it on or not. To remove this, we actually replace this with open circuit and find voltage at this point to see whether this V is greater than or equal to this fixed value of Vz, and from that we can check whether the diode is on or off. So through this equation, which is from voltage divider rule, we can find the value of V, that is RL VI over R plus RL. So by substituting the values, we find that V is equal to 8.73 volt. That means here only 8.73 volts appear by this RL resistor and by this input voltage Vi. So V is equal to 8.73, which is less than Vz is equal to 10 volt. At least here we should have 10 volt to turn this diode on. So it means that diode is in off state. So when diode is in off state, we replace the Zener diode with an open circuit. And you can see through this characteristic curve, we are somewhere at this point where diode is off and there is no current flowing through the diode, and in this case we replace the Zener diode with an open circuit. Now we can find other circuit quantities, which are VL is equal to V, that is equal to 8.73 volt. VR is equal to Vi minus VL. VR, which is here, we can find it by subtracting load voltage from supply voltage. 16 minus 8.73 equal to 7.27 volt, and we know, since this is an open circuit, Iz is equal to 0 ampere, and Pz, which is power being dissipated by this Zener diode, is equal to 0 watts. Now in its B part, now we have RL equal to 3 kilo ohm. Let's calculate V again by substituting open circuit at the point of Zener diode. So calculating V will give us 12 volt. Now V is equal to 12 volt. If you replace RL with 3 and multiply it with Vi, which is 16 volt over 1 kilo ohm, the value of this resistor, and 3 kilo ohm, the load resistor, we will get 12 volt. Now this V is greater than 12 volt. That means actually V is equal to 12 volt. That is greater than Vg, which is 10 volt. That means diode is in its on state, and we should replace the diode with an equivalent circuit which is 10 volt voltage source. Now we have replaced diode with this equivalent circuit of 10 volt, which is equal to Vg. So if diode is on, 10 volt voltage is being dropped across this diode, and we know voltage remains same in parallel. So VL is equal to Vg equal to 10 volt. Remember, this calculation was just to check the diode, whether diode is on or not. Now if diode is on, the voltage across the diode cannot exceed the value of 10 volt Vg. So Vg is equal to VL is equal to 10 volt, and Vr is equal to Vi minus VL, that is 16 minus 10 volt is 6 volt. Vr is 6 volt, and IL is equal to VL over RL, that is 10 volt over 3 kilo ohm, 3.33 milliampere. This current is flowing through the load resistor, and IR is VR by R, 6 volt divided by 1 kilo ohm, 6 milliampere. We can find Ig, that is IR minus IL, 6 milliampere minus 3.3 milliampere, that means 2.67 milliampere current is flowing through this Zener diode. And we can calculate power being dissipated by this Zener diode with this equation: P is equal to Vi, that is 10 volt Vg into current flowing through the diode, 2.67 milliampere. This is equal to 26.7 milliwatts. Now the second condition which uh, uh, we can see is fixed Vi. Here the input voltage is fixed, and we have a variable RL. A variable RL means we should find the range of load resistor values which turn on the diode. So by range, we mean we should find a minimum value of RL and a maximum value of RL. So to find the minimum value of RL, we use this equation again, since we know the minimum voltage required to turn this diode on is V is equal to Vg. That means VL should be equal to Vg at least to turn this diode on. So by putting in this equation, we see the RL minimum which is derived from this equation is equal to R into Vg over Vi minus Vg. Now since we have find the minimum value of RL, that means the current flowing through this load resistor will be the maximum. That is, IL maximum we find through this equation is Vg over RL minimum. Vg is equal to VL since we know voltage remains same in parallel. Once the diode is on in the on state, the voltage across R remains fixed. Once this diode becomes on, we know in this portion of circuit the voltage is Vg and here we have Vi. So the voltage across this R will be Vi minus Vg. So Vr is equal to Vi minus Vg, and we can find IR, which is current flowing through this R resistor, is equal to Vr over R. And Ig we know we can find with this equation. Ig is equal to IR minus IL. Now to find maximum value of RL, which actually turn on this diode and which does not violate the PG maximum condition. PG maximum condition is it means that this Zener diode should not dissipate power more than this value. In other sense, we cannot allow current which is Ig which is greater than Ig maximum. If that happens, this diode gets damaged or burned. So to find the maximum value of RL, that is, if we have RL maximum, we should have IL minimum. We know larger resistor will allow lesser currents. So IL minimum will be equal to IR, which is fixed for on state of diode. This is fixed because VR is fixed. So IL minimum is equal to IR minus Ig maximum, and RL maximum can be found with this equation, which is Vg. Vg will appear against this load resistor divided by IL minimum, and we find IL minimum through this equation. So in other sense, we have derived equation for a minimum value of RL and a maximum value of RL. That means we found a range of RL. Now the third condition is fixed RL and variable VI. Here we have RL, which is load resistor, that is fixed, and we have VI variable. So now Vi is variable, we should find the range of Vi we turn on the Zener diode. So we should have a minimum Vi and a maximum Vi. So for the minimum turn on voltage Vi, which is equal to Vi minimum, we can determine this by this simple equation. When diode is on, and for the minimum condition, we should have VL equal to Vg, and we find this by this equation RL Pi over RL plus R. Now here we have Vi equal to Vi minimum. From this equation we can derive this equation Vi minimum, that is RL plus R into Vg over RL. This is simple calculations. Now we have equation for Vi minimum. For Vi maximum, we know that uh, there is a maximum current IgM which should flow through Zener diode. That means no more than that current should be flowing through Zener diode for the safe operation. Since we know IR is, that is actually total current, is equal to Ig and IL, so that means IR maximum, which will be against Vi maximum, is equal to Ig maximum plus IL. Now we know IL is fixed. Why IL is fixed? Because RL is fixed, and when diode is on, we have VL equal to Vg, which is against fixed. So V and R both are fixed. That means IL is fixed. So this implies the value of total current will be depending on the Zener current. So the maximum total current will be against the maximum Zener current. Since IL is fixed, because Vg by Rg, and Ig maximum is the value of Ig, the maximum Vi is defined by Vi maximum is equal to Vr maximum plus Vg, and Vr maximum we know is when Ir maximum into is multiplied by 2 the value of R. So we can find Vi maximum from this equation, that is Ir maximum into R plus Vg. There are few examples in your textbook. You can solve those examples to have a deeper look how we can find different circuit quantities for these different conditions.